This is Shakil Ahmed. In this video, we will discuss about linear mixed effect models in R. Uh, First, we will discuss what is linear mixed effect models and why we need linear mixed effect models, and then show what we are going to find in this tutorial, and then we will go to the R codes. This is a slide I have created through Quarto. That's why I just mentioned. So linear mixed effect models are basically the alternative of classical linear regression models, where the error terms are correlated. But when we have correlated data, for example, in case of repeated Mayer's observation, we have data on uh, repeated data on a single patient. For example, when we measure something uh, at many times for a single patient, or we have a type of clustered data when we have patients are more similar in one center in one hospital than other hospitals. So in such type of data, we can't apply the classical linear regression models. Basically, linear mixed effect models account for the correlation structure among observations by including the random effect in the model instead of the only fixed effect model. It has two parts. And the linear mixed effect models are specifically designed to handle the longitudinal or repeated metadata. Although you can also use for the cross-sectional data when we have clustering, we have uh, correlated observation within certain clusters. The linear mixed effect models incorporate the random effect in addition to the fixed effect, and the linear models provide more flexible in modeling complex data structure and can handle nested or crossed random effects. And this is the structure of a linear mixed effect model, where we have two parts, one the fixed part and the second is the random effect part. The fixed effect means we have constant effects for the variable axis on y, and that is irrespective of the models, uh, irrespective of the groups. And the second part depends on the group specific effect of for example, it is mentioned as gamma, uh, that is depending on z is basically depending through gamma on y, and gamma is basically a random variable instead of a fixed variable, and z is covariates associated with a random effect. For example, if we have data on different hospitals or in different locality, different counties, then these that quantities related covariates and that are affecting the outcome of interest. And E is the random error term that is at individual level, not at cluster level. So fixed effect represent the average effect across all groups or subject in the data, while random effects capture the variability between different groups or subjects in the data, and we need to capture those variabilities uh, between different groups while modeling the effect of certain exposure on outcome. So here is the result of fixed effect model, random mixed effect model. We will discuss later, and this is diagnostic plot, that is the plot between observed value and the predicted outcome. And this is the plot for checking the variability in intercept across the groups. And these are some other just a table created in Auto document. I will discuss in a next video how we can produce such tables. So we start with for linear mixed effect model. We need to install LME4 package. I have already installed, so I just skip it. And I am again using the heart disease data, which includes can just run and see what variables we have. DF. So we have variable on age, sex, blood CP, and chest blood pressure and cholesterol level and other different markers. And the target is the heart disease status. But we are basically working with linear mixed effect models, not the generalized linear mixed effect models. So we are assuming that the outcome of interest is uh, continuous rather than dichotomous. So we just take the thalage, that is maximum heart rate, as our dependent variable, and the resting glucose and cholesterol, age, and sex are taken as the fixed effect covariates, and we are taking the thali- thallium groups, basically that is related to thalassemia. Are those groups are taken as clusters. We have different groups. You can check. Uh, we have 0 to 3 groups, 0, 1, 2, 3, 4. So I'm just taking those groups as clusters or groups, and definitely patient within those groups will be have uh, similar maximum heart rate. Uh, that's why we are taking these groups as clusters, and we can just summarize the. We can first run the model. This is a linear mixed effect model in R, that is the LMER function. This function is under LME4. And now you can see the model which produce the random effects. These are the variability variance in the random effect intercept, and these are the error variance. Basically, these are uh, variability between according to for area specific variability, and this is individual specific variability, and these are the standard deviation for the variances, and there are total number of observations, and there are 4 groups, and we have these are the basically effect of interest. We are basically uh, observing the effect of different covariates on maximum heart rate. Cholesterol is not cholesterol is significant, but the resting glucose is not significant. Age is significant, and sex is also not significant. So these are the effects of the cholesterol level on maximum heart rate, age, and sex after incorporating the variability within groups. Basically, that is the variability we might have 57.71, which is because of the different group difference in the patients. So this this is required to take into account the variability between area, between clusters, while uh, assessing the effect of fixed covariates or covariates on the outcome. And we did it using the linear mixed effect regression model. And you can also see the correlation between the fixed effect. If there are the fixed effects are highly correlated, then we need to check for other, although there is no significant, there is no strong relationship between these effects. And now you can plot the predicted value versus the observed value, that is thalage, that is maximum heart rate, and the predicted maximum heart rate. We can just need we are just calling the library ggplot2 and then making a plot, find the predicted values, and if you want to see these are the predicted values for uh, the y accounting for the between cluster effects variability. So you can see these are the predicted maximum heart rate for different patients. So this is an interesting model which is called nested error model, where we have a nested structure in data. For example, we have first the sample of clusters, and then within clusters we have different observations, different patients, or we have different time points that can be considered as groups, and within for a specific time point we have data on different patients. So basically we can take patients as the uh, groups, and then repeated measures within patient can be taken as the individual observation. So we can, on for that type of study we can take uh, either time as the grouping variable or the individuals as the grouping variable, and within observations within individual can be taken as individual observations, and we can see the effect of covariates on the outcome for such type of data. Clustered data or longitudinal data. Longitudinal data means we have different observations for a single patient, and we have different number of patients. So this is just a correlation structure. More there will be the correlation between the observed and the predicted values. We can say that we have more flexible, more appropriate model. So this model is just written, and this is a line which is taken as at the intercept is equal to 3 and slope is equal to 4. It means we are taking maximum heart rate is equal to this for predicted maximum outcome 0, and then taking the slope 1 we are drawing a straight line, AB line. So this is basically showing the trend between the maximum heart rate, observed maximum heart rate, and the predicted maximum heart rate, and we can see there is a increasing trend between the two values, the observed value and the predicted value. And then we can also see a dot plot to see which group has more variability in intercept. For that we need the library lattice, and then we can make a dot plot, and that is we can also say a forest plot, and this will tells on x-axis we have the the difference of the intercepts from 0, and on y-axis we have different groups, group 1, group 0, group 3, group 2. So we can say that there is small variability in group 3, and group 2 has also small variability, but this is quite far from the 0, and group 0 has highest number of variability, highest variability in intercept. So these are the things about the linear mixed effect models. If you have any question, you can always write in the comment box. Thank you.